Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And today I'm going to talk to you about the 737 Pneumatics System. So this presentation, I'm going to take a high-level look at the pneumatic system on all models of the 737. For the sake of brevity, I'm going to cover air conditioning and pressurization in other presentations. I realise that these have been rolled into one in FCOMs of recent years under the category of air systems, but back in the day they were divided out into air conditioning, pressurization, and pneumatics. And I think for a refresher or to learn these systems, it's probably better taking them individually in bite-sized portions. So that's what we'll do today with this presentation. And then the next one will be on air conditioning, and then the one after that will be pressurization. That way we've got all the air systems covered. My usual disclaimer, always treat your company training and manuals as the authoritative source of information. So as an overview, the pneumatic system, it can be supplied by either engines, the APU, or a ground source, any of those three sources. And it supplies air conditioning, pressurization, as I've already said, and again, these will be the subject of individual presentations in their own right soon. Engine starting. That photo there, for those of you who haven't seen it, obviously that's under the cowl of a CFM 56. The large silver duct that you see coming down vertically from the top, that's the pneumatic manifold for the engine start, and the start unit is that grey box with the circular unit on the front. So that's what the engine start unit looks like on a 737. It also is used for engine and wing anti-ice. For the water tank too, to put a head of pressure on that. Hydraulic reservoirs. The auxiliary fuel tanks. Aspirated TAT probes. And the inert gas system. So they're all the things that pneumatics supplies. Most of these I will look at in detail in their own presentations, be it hydraulics, fuel, what have you, but the actual air supply we will cover here in pneumatics. Okay, so let's start at the beginning with the source of the air, which is for the purpose of this, the engine bleed air. Those of you that have my book may recognise the start of this schematic as being part of a large and complex one. What we're going to do is we're going to build it up slowly in parts, so that you can see how it came about and you can put it all together in your head. So, engine bleed, as we probably know, it's taken from 5th stage, supplemented by 9th stage at low engine speed. On the max with LEAP engines, that's 4th and 10th stages respectively. 9th stage is used as and when required, so low fan speeds. Downstream of that, you've got the bleed valve. From there, that feeds into the right pneumatic duct, and you can see you've got an isolation valve there and pneumatic duct pressure between them. So that's all straightforward so far. The engine bleed air is actually pre-cooled. That pre-cooler comes from the fan air. You've got a control valve there. And beyond the pre-cooler, that's where air is taken from for the engine start. So those two are drawn in now. Engine anti-ice is taken from before the pre-cooler. This is the only pneumatic service which is taken before the air is pre-cooled. Obviously you want that air pretty hot to have maximum effectiveness, so it's taken before the pre-cooler. Now this, I should reiterate, is just engine anti-ice. Wing anti-ice is taken after the pre-cooler because it's got a longer duct run to do. Okay, you've got a pressure and a temperature sensor here. The pressure sensor is before the bleed valve, so that in the event of an overpressure, you can switch it off there, and you know what the pressure is before that bleed valve. So that's 220 psi on the pressure. The temperature is picked up after the pre-cooler, so there's actually no way of us knowing what the temperature of the air pre-cooler is, but nor would we need to know it. The temperature switch is after the pre-cooler, and out of interest, it's 254C. The ground pneumatic source feeds into the right-hand pneumatic duct, and you can see that marked on at the bottom. And again, I don't wish to insult anybody's intelligence. You know, those of you who've been flying the 737 a while, but it's certainly a common error amongst new guys coming onto the type, or folk who the 737 is their first airliner. They do get confused that there is actually a difference between the ground pneumatic air for starting the engines and the preconditioner for warming the cabin. So just to be absolutely crystal clear, this is where the air goes for starting the engines. Wing anti-ice, you see I've had that on down there. So for the right wing, that air comes from the right pneumatic duct. For the left wing, it comes from the left pneumatic duct. APU bleeder is fed into the left pneumatic duct. And then what I've done is I've shown here the other pneumatic services. So looking just below the left pack valve there, you can see we got a feed for the turbofan. This is on the classics only, just to increase the airflow through the packs. What I've labelled as AF, simply because I ran out of room, is auxiliary fuel. Then there are the hydraulic reservoirs, A on the left, B on the right, the water tank, and NGS is nitrogen generation system, or inert gas system, for those of you who haven't got it on your aircraft yet. And this is all taken before the pack valves. Note the minimum pneumatic duct pressure to ensure the normal operation of all these systems is 18 psi. Okay, then I've added on the mix manifold. So this takes in air from the packs and the recirc fans, and ground conditioned air if we have it. Now, this is the ground conditioned air for keeping the cabin warm, and it mixes it before distribution. Packs. Now I've only drawn on the right pack just so that this doesn't get too busy, but you can see that after the pack valve, the air then goes through an air cycle machine, and it is cooled also by ram air through heat exchangers. Inside the pack there's also a water separator that collects any water that's condensed by the cooling process, and that's extracted out to avoid any icing downstream of this cold air. I'm going to cover packs in much more detail in the air conditioning presentation, but this really is just an overview. It's difficult to talk about pneumatics without mentioning the packs, but that's all I'm going to do on this presentation. Trimmer, again, this is an air conditioning thing, but just to put it on, just so you can see the whole build-up. Trimmer is only used on long body aircraft, so that's the 4, 8, 9 and the MAX aircraft. Basically it's added to the two zones which you selected to be warmest. Again, I'll cover this in detail in the air conditioning presentation. Flight deck air, just as a reminder, this comes from the left pack. It may contain trim air, so flight deck air does not come from the mix manifold. And there you go. Once you add in the left-hand engine and a full view of the panel, that is the whole pneumatic system schematic laid out right there. looks quite complex when you put it all together, but as you've just seen, when you build it up in bite-sized portions, it's actually very straightforward. Okay, so looking at the pneumatics panel itself, let's start by taking a look at the individual captions. So dual bleed, this is warning of possible damage to the APU in a nutshell. And this will illuminate whenever the bleed and isolation valve switches are positioned such that the engine bleed air could enter the APU. I've drawn this on with the two red arrows down at the bottom there. So the two situations that you can get this are either engine 1 bleed on and APU bleed on, so that's the short route, or engine 2 bleed on, isolation valve auto, and the APU bleed on. In either of those cases, the worry is that engine bleed air, which is more powerful than APU bleed air, could back pressure the APU, causing damage. Now, the obvious solution to this is to reconfigure the panel accordingly to remove that dual bleed light, either with engine bleeds, or the easiest one is with the APU bleed. If for some reason you can't do that, you need that configuration, then your only other option is to try to reduce thrust to prevent damage. But again, it depends on your circumstances, your phase of flight, what you're doing as to which option you take. But usually the easy win is to switch off the APU bleed. Okay, next slide, we're going to look at wing body overheat. I'm going to skip pack light. Again, this is an air conditioning light, not a pneumatics one. So straight on to wing body overheat. Now, this is potentially a fairly dangerous one. This indicates a leak in the corresponding bleed air duct. It's particularly serious if the leak's in the left-hand duct, because the left-hand duct also includes all the ducting back to the APU. The duct runs are quite short on between the engines and the packs. But going all the way down to down the keel beam to all the way the length of the fuselage to the APU is the left-hand duct as well. So a leak there could do quite a lot of overheat damage in the cabin. The wing body overheat circuits can be tested by pressing that overheat test button up there on the right-hand side. Press that for a minimum of 5 seconds and both wing body overheat lights should illuminate. Now, this test part of the engineer's daily inspection, but I mean, you can do it if your company procedures allow you to. I mean, no bad things will happen. Do it on the ground, press this, and the wing body overheat should illuminate within 5 seconds. Next pair of lights are bleed trip off. And as I've already mentioned, and you saw in the schematic, these will illuminate, i.e. the engine bleed light will trip off if the pressure exceeds 250, so 220 psi, or the temperature exceeds 254 C. Now, note that unlike the wing body overheat lights, bleed trip off lights are only applicable to the engine bleed. So whereas wing body overheat on the left-hand side also included the duct run down to the APU, the bleed trip-off on the left-hand side does not include the APU. So it's not indicating an APU bleed trip-off. There is no such light. So these are purely for the engines. So I say, if you get the over pressure or the over temperature, the bleed valve light will close, the light will come on. As we know, there are two reasons why this could happen. It could be an over temperature, in which case just leave it for a moment or two and try the trip reset button, which is located between the two trip off lights. That may work if it's been an over temperature condition. Remember the valve was before that. If you stop that hot air going through, it'll cool down and you can trip reset. If it doesn't trip reset for that, then it might have been an overpressure condition. These are most common on when the pressure is highest, which is full thrust, bleeds off takeoffs. And this happens because you get a leakage past the closed high stage valve, butterfly valve, which can lead to a pressure buildup at the downstream port on the overpressure switch in the high stage regulator. So the in-flight fix for this is to reduce the duct pressure. So how would you do that? A couple of ways. You can reduce thrust. Now you can either do this with thrust levers, or you could possibly select climb too, or you can reduce the duct pressure by using pressure sources from before this. So engine anti-ice or wing anti-ice will reduce the duct pressure. Even if you don't need it, just try putting on engine and or wing anti-ice. That'll reduce your duct pressure, and you can trip reset and away you go. Okay, next item is the isolation valve. The left and right pneumatic ducts are normally split. They're normally isolated, and you see this by a duct pressure split on the duct pressure gauges there. So if they're split, then the isolation valve must be closed. With the isolation valve switch, which is a 3-position switch on, auto and close, with that in auto, the isolation valve will only open when either a bleed air or an engine bleed air or a pack switch is selected off. Any one of those will open the isolation valve. Okay, we've already mentioned the external air for engine starting. This is what the hatch looks like. Obviously, as pilots, we very rarely see this hatch open because the ground crew are doing it while we're on board trying to start the engines. Just a reminder, this air feeds into the right pneumatic duct, and logically or perhaps logistically, this hatch is on the right-hand side of the fuselage. The aircraft really is built the way the schematic looks. So this hatch is on the lower right-hand side of the fuselage, near the wing leading edge, and it's very close to the engine inlet for engine number 2. I mean, it's only, you know, the distance between the engine and the fuselage. We're talking a matter of feet. So for that reason, if you're doing an external start, you must start engine number 1 first, so that this external air can be safely disconnected by the ground crew. So that's what that hatch looks like. Ground conditioner, this is the other one of the pair. This is the one for keeping the cabin warm on a either keeping the cabin warm on a cold day or keeping it cold on a warm day. It does both. And the hatch for this is directly under the centre of the fuselage, in front of the wheel well by about 4 or 5 feet, and that is exactly where the mixed manifold is. That is a very short run indeed, inches to the mixed manifold. Okay, so coming back to air for the other services, looking here at the hydraulic reservoirs, the photo actually shows a B reservoir pressure. About 10 years ago, these two were combined into one. So on 737s newer than 10 years, all those that have had the retrofit, you now only see one of these gauges, which simply says reservoir pressure. So what's this all about? It's used to simply keep a head of pressure on the 2 hydraulic tanks, the hydraulic fluid tanks, and this avoids foaming. Now, foaming, when you climb, the pressure reduces, the air pressure reduces. And if you don't keep the liquid under pressure, what will happen is that any air that's dissolved in the liquid will start to bubble out. Now, if it bubbles out and goes to the top of the tank, that's not a problem. If it bubbles out in the lines from the tanks to the pumps, that is a problem, because that way you will get air in the pumps, and if there's enough air, then the pumps can cavitate, and if they're cavitating, they won't be working, and the pump will fail, and you will lose hydraulic pressure from that pump. So this is not good. Cavitation, if you've not actually seen it in action, the thing I always notice is if you've got a bottle of water with you in flight, and you open the bottle of water atop a climb, you will see the air bubbles rise out of it. That's foaming in quick time. If you were to open the bottle of water on the ground, leave the cap loosely on, and climb, when you take the cap off, you wouldn't see the bubbles, because they'd have been coming out at slow time in the climb. Anyhow, I digress. So this is the issue. Now, again, for the beginners, and I don't want to insult any experienced pilot's intelligence here, but this is hydraulic reservoir pressure. This is not hydraulic pressure. Hydraulic pressure is the pressure of the hydraulic system after the pumps, which is 2800 to 3000 psi. This is simply a head of air pressure on the tank to ensure the continuous supply of fluid to the pumps. And as you can see from the green arc there, it's typically 44 to 50 psi. I think from memory that there's an overpressure relief on this at about 65 to 70 psi, but it is not the same as the hydraulic pressure of the aircraft. Air for the water tank and the auxiliary fuel is used in a similar way. Not exactly the same, but it's actually a very similar way. And the minimum pneumatic duct pressure to ensure the operation of these systems is 18 psi. Sidewall risers. I was in two minds whether to include this in this presentation or aircon. I've got it in aircon as well, but it's such a long length of pneumatic ducting. I thought it would sit well here. So the sidewall risers, they take air from the mixed manifold, which we now know where that is because the ground conditioned air, up to the top of the cabin for distribution amongst the cabin vents. And how it gets from the bottom of the fuselage to the top is around the side of the fuselage, and you can see exactly where it goes by the missing passenger window. And as you can see from this variety of aircraft, the short-bodied aircraft, so the 3, 5, 6 and 700, have got one riser on the left-hand side. Long-bodied aircraft, so your 4, 8, 9 and the MAX, have got two risers on the left-hand side. And those the risers on the left, on the short body, it goes forward. The risers on the long body, one goes forward, one goes back. All aircraft, all 737s, have only got one riser on the right hand side, and that goes aft. There you go. Quick look at max differences. The bleed air control system is digital. This is a huge difference on the Max. It's now got an electronic controller, so you can digitally tune the amount of air that's needed, and amount is the key word, because the previous system, when you put the selected engine or APU bleed air on or off, that was it. It's all or nothing. It's either no bleed air from the engine or all it can give. Now, 9 times out of 10, it's giving more than you need. So it's taking more bleed air out of the engine. And as we know, if you're taking more bleed air out of the engine, then you're losing out you're taking a hit on engine performance. So for takeoff, that's a hit on engine performance, which could be runway or payload limiting. In flight, it's not performance per se, but it's fuel burn. So using this digital system, it gives better aircraft performance for the takeoff and landing stage, and it increases get the sense right, it reduces fuel burn in flight. So it's a very good improvement on the Max. The bleed trip-off lights have been replaced by a new bleed light, and this can indicate several things. First of all, pressure or temperature is too high, and that is the same as the old bleed trip-off light. The new one of the three here is an under pressure. Or it can indicate that there's a failure in the bleed air system, so that this is new, or that there's an incorrect bleed configuration after takeoff or go around, which is also new. So there are your max differences there. It's a significant improvement. Okay, that's it for pneumatics. I say it's been a little tricky to talk about this without including aircon and pressurization and the other services, but they will be coming soon in the next video, which I'll be releasing next week. As ever, if you've enjoyed this video, please like it and subscribe to my YouTube channel. The address is given down there, or you can click the link at the bottom right. Thanks for listening.